Okay. Good morning, everyone. Should have actually had it before, sorry. Want to show you how to deal with the peer review. Forms. So let me get one of them up. Okay, so here's your form. What you're going to do is ignore the column that is about it that has your name. So each group has one of these files. Ignore the column about yourself. It doesn't matter. I mean, you can fill that as well, but we're not going to take it into account. And then just rate your peers. And if you have any comments for them, write your comments down below here. So the one that we care about the most is your overall contribution. So the rest of them are just feedback plus the comments. The one that we care about is the last one, the overall contribution. Now, after this form is submitted, the deadline for submitting this form, if you are not going to use your any grace days, then the deadline for you is 1 hour after the lab's deadline. If, however, you're going to use grace days, then the deadline for you will be extended by the grace days. So the deadline for you becomes 1 hour after you submit your late submission. Once this is submitted, we run our scripts. We extract these numbers. We average the contribution factors for each member of the group. And then we will send feedback, anonymous feedback, to every single person in the group, which is basically we send you the comments that your group mates have for you anonymously, so you wouldn't know which group mate has made what comment. And we also send you the average of these numbers so that you know how your group mates think about different aspects of your work. I think that's enough with that regard. Okay, when is that quiz due? Look at the website for the deadlines. Nice shave, thank you. Do we need to have comments for our peers? You don't have to have comments, but it's something that people would appreciate. Just receiving some number is not that informative. If you have informative comments, if you have a comment that you think is going to change this, change something, I would definitely put that comment there. Or if you want to reinforce something good about someone. So your teammates will get anonymous feedback. So look at this peer review as a means to help you have a healthy group that achieves the goals, and everybody benefits from participating in it. Okay, now let me jump into the lectures. We're a little bit behind, unfortunately. I keep saying it. I should drop saying this, but anyways. Okay, so we're talking about the last concept of operating systems, which is dual mode operation. Okay, so I received questions and I will answer them. Once I'm done with the topic, I go back and answer the questions. So you keep sending me questions, that's fine. Okay, so we said that we want to have a kernel mode and a user mode. How do we implement them? You can implement user mode and kernel mode in software, but usually to have high performance, have efficient implementation, we use hardware support. Hardware support usually gives us efficiency and performance. So usually hardware provides this for us. Okay, so there is messed up a slide. Okay, so there are 3 types. So this is a conceptual classification of these 3 types. So with 3 events, we switch from user mode to kernel mode. What are them? So the first one is system call. So this is when a user program requests a service from kernel, like open a file, close a file, read a file, write to a file, open a socket, send a packet, all of those. These are system calls. So every time a system call is called, we trap to the kernel. Usually, again, not all the time, but usually we in the system library, we execute a trap instruction. Usually it's called trap. Some system call it syscall. And that instruction transfers, when the processor sees that instruction, it transfers control to the kernel, and then the kernel will take care of it. We'll talk in details about system calls. The second event that could cause a transfer of control from user to kernel is processor exception. So these are internal synchronous hardware events that usually are caused by software behavior. For example, you could divide by 0. So this is a synchronous. When I say synchronous, I'm talking about the code. So the code causes this because of its behavior. It's a result of the actions of the program. Or let's say that your program accesses a location that it's not supposed to access. Let's say your program tries to change its code and the code is read-only, right? So these are the things that trigger exceptions, and we call them processor exception. And the last one is interrupts. So this is an external and asynchronous event. It doesn't depend on your program. Let's say your program is running and then you know, somebody clicks a button. So this is an interrupt. So now the control will go back to the kernel to take care of this event, or a packet comes, or a file is ready. So these are asynchronous and external events. Now, you might actually see all 3 of these events being called exceptions. Sometimes, usually people call the first 2 synchronous exceptions and the last one asynchronous exception. But I'm putting aside that definition. We're going to go with this definition. So we're going to call them system calls, processor exceptions, and interrupts. And these are concepts. we're not talking really about their implementation. We're talking about these 3 events that could happen. Now, how do we deal with them? How do we implement them? It will come next. Oh, one thing I forgot to mention is that usually you can mask interrupts, not letting them happen. You could say, I don't want to be interrupted, but usually you cannot do that with exceptions and system calls. You cannot mask exceptions, because if you divide by 0, your processor is the exception happens and it has to deal with it. Yeah, so here, one example that you might want to mask exceptions is when you are actually dealing with one. Mask interrupts is when you are dealing with one of them. Let's say an interrupt has happened, so you're handling an interrupt. You probably want to mask in other interrupts. Otherwise, you could potentially get interrupted inside your interrupt, and then you start that one, and then you get interrupted within that one, and then you could actually have a stack overflow, for example. So you want to mask interrupts, take care of one, and then go with the rest of them. Here is an example how masking happens in x86. You can execute CLI to disable interrupts, and then STI to enable them back. Now, when an exception happens, when any of the 3 events happen, system call, processor exception, or interrupt, what happens is your processor has to handle them. Well, how do the processor know what to do? Well, the kernel has to tell processor that if this event happens, start running this code. If this event happens, start running this code. And if this event happens, start running this code. And we call the table that contains this information, we call that an interrupt vector table. It's usually somewhere that the processor knows. So kernel field data in that table, and then processor just reads and follows the instructions. So here, what is one example? It says, well, if timer interrupt goes off, the kernel has told the hardware to run this code. So there's an address here that points to this code. And when that event happens, hardware knows that it has to look into this entry to find the address. So if operating system doesn't fill this up, then that event doesn't get handled. So yeah, I guess this is a good place to answer questions before I move on. Okay, when will the quiz grades come out after the deadline? Which lectures will the quiz be on? As mentioned, each quiz will be covering everything up to the point of its release. Would we be able to take the quiz after today's lecture? Yeah, the quiz doesn't cover today's lecture. So it covers everything before its release day, which was yesterday, Monday. Is catching exception considered masking exception? No. When you catch exceptions, so here's catching exceptions means handling them. It doesn't mean masking them. Masking means that don't even bother telling me that this has happened. Okay. And yeah, okay. Now, how do we implement this now? The first thing that we have to keep in mind is that when we're transferring control from user to kernel, we have to be really careful, because we don't want a malicious, buggy program that was running to come and, because of this transfer of control, mess up with kernel code. Because as you might imagine, we might actually get some inputs from the user program. For instance, if it's calling system call and it's saying, open this file for me. So that's an input. Now, we don't want the user program to be able to, by inputting to the kernel, giving inputs to the kernel, mess up with the kernel. Or we don't want the user program to be able to jump anywhere that it wants. We want it to be controlled. That's why we have that table, to make sure that when the transfer happens, we're actually, every time we're starting from a given point. Let's say handling timer interrupts or handling an exception. Now, that's the first thing that you have to, that's pretty much our goal, to make it a controlled transfer of control. The second point is, well, if we are going to have some inputs, and if we are going to actually make sure that any buggy program is not going to impact us, so now look at the exception handler or any system call handler. They are kind of like a function, right? It's a function that is going to call, it's going to be executed. Now, each function needs a stack. You need to have a stack to run. Now, the question is, what a stack should I use? Now, we know that each program that is running has its own stack that is growing and then shrinking based on calls. So the question is, can we use the stack of the user program? Let's say they push the input on their stack, and then they call a trap instruction to use a system call to ask for a system service. Can we just use the stack of the user? The answer to that question is, if you really want to implement controlled transfer, and if you want to have a secure software, a secure kernel, the answer is no. Now, you might ask why. I'm actually transferring control to kernel. What can possibly go wrong? The thing about it is that, let's say you have a multi-core and you have a actually forget about multi-core. Let's say that you have a multi-threaded application. As I mentioned previously, threads within one process have access to each other's stacks, because a stack is part of the address space. Now, let's say one of them asks for a service. We come to the service, and then at some point we context switch to another thread. So this other thread has access to the stack of the other thread. And even if we checked everything on the stack when the interrupt happened and everything was fine, we cannot trust that stack because other threads have access to it. That's one example that things could go wrong. So we don't want them to be able to manipulate the stack after we check it. So the way to actually do it in a safe way is to have one kernel stack alongside the user level stack for each thread. And every time we want to run kernel tasks, or kernel functions or kernel code, we just use kernel stack. And kernel stack is in the kernel address space, so no user has any access to any kernel stack. So we basically make this distinction. We don't allow users to mess up with the kernel stack by just using a separate kernel stack per thread. So how does this work? We'll talk in details about it. You're going to actually implement it. in the labs, in lab 2. The way it works is every time you create a new thread, you're going to create user stack, you're going to create heap for that, you're going to do all of that for that thread. You also will make a kernel stack for that thread. So the kernel knows the address of this kernel stack. You could keep it in your TCB, for example. And every time you make the switch, you use this stack for kernel code. I keep getting questions. I'm just acknowledging. I will answer, definitely. OK, let's talk a little bit more about it. So every time on a system call, exception, or interrupt, what's going to happen? So hardware is going to be receiving the event, right? And when the interrupt or exceptions or system calls happen, usually hardware disables interrupts and then switches mode, basically flipping that bit. So it was in the user mode. Now it flips the bit. It's now in the kernel mode. It then looks at the table. It finds the code that it has to execute. So sorry, actually, before that, it also saves the PC. So we were somewhere in the user program. We have to save it. Now, what does that mean, saving PC? Well, it's hardware dependent. So x86 does it differently than ARM. So in ARM, as you probably know by now, you have banked registers, at least the processor that you're using. That basically, when the switch happens, your PC is saved in banked registers. In x86, things are different. I actually have a slides for it, so we'll go through that. So what does it exactly mean to save PC? But let's say we save the PC where we were, and then we jump to the code that we have to run. Basically going through the interrupt vector table, finding the function that has to be the handler that has to handle the event. And when some processors, other than saving PC, the hardware might also save some other registers. As you know, again, in ARM, for instance, by having banked registers, we're actually saving more than one register. x86, the same. So again, I will show you what x86 does. And then once you're inside the handler, you actually save the entire state of the thread that was interrupted or caused an exception or asked for a system call. You have to save the state, which we'll talk in the next slide. So this is an example on how things work. Let's say I'm running a thread. So in the creation of this thread, I created 2 stacks. So this stack lives in kernel address space. So user program has its own address space and has no way of accessing this stack. The one that the user program has access to is this user stack. Now, let's say we start the main. Let's say we call process 1, like it's a routine that we call, then another function call, and then at some point we call system call. Let's say we want to open a file. So at this point, what happens is that we trap to the kernel. Now, the first thing that is going to happen, let's say at this point, we're actually handling the system call. So what happens is usually the handler saves the CPU state, basically saves the state of the program or process or thread that was interrupted or called system call or caused an exception. So we save the state. So as you can see now, we're running kernel code. As a result, we are using the kernel stack. We're not using this stack. We don't touch that stack anymore. So everything that kernel does, it does it here. It saves the user CPU state, and then it starts running the system call handler. At some point, we might actually have to run the driver code again, driver is running in the kernel mode, so it uses the kernel stack. And let's say at some point we're done with the driver, and then we're done with the system call handler, and now we're ready to go back to the user. So what happens then? So what happens is eventually at some point we're going to go back to this thread sometime, not necessarily right after we finish the handler. We might at this point go to someone else, but eventually, again, we have one kernel stack usually per task or per thread. So we're not going to touch this anymore at this point until when we want to go switch back to the thread. So any moment that we want to do that, now we have the user CPU state saved on the kernel stack. So what we can do to transfer back to the user, we can just fill the registers with the copy that we have. So we just copy them back to the CPU. At this point, after we copy, the state of CPU is the state of CPU when this happened. So the user program can continue running without even noticing that all of this happened, because we didn't even touch the stack. We just at this point the system call returns, so it pops up its stack frame. Okay, I guess this is a good time to answer questions, and then I'll continue. So is it just me, or this slide doesn't exist in the slide deck provided? I don't think. You might have the old version. I have actually revised, so you might have downloaded this previously. Always check the GitHub repository and make changes. So yeah, I'm pretty sure it's there, and if it is not there, I'll put it there later. Okay. What is an example of an invalid stack pointer, and why would this be a concern for reliability? Yeah, so let's say you know, your stack pointer has overflown, or your stack pointer, you can, as a user, you can actually change your stack pointer by just writing or reading in it. Let's say you have a multi-threaded program, you go further than what is allocated to you. Now your stack pointer is not valid anymore. It's just something that it shouldn't have been. And if kernel uses that stack, basically it means that it's using that stack pointer, and that is bad, right? That's not, it's against reliability, because if, let's say it was a multi-threaded program and now your stack has overflown, it's inside somebody else's stack. Now, if if kernel uses this stack and starts writing in it, then at some point runs another thread, then another thread could overwrite kernel stuff, and that's against reliability. That was a good question. What's the difference between the kernel and operating system with respect to the different modes? As I said, operating system is set of, the definition of it is basically by set of responsibilities that operating systems have to provide and support. Kernel is the code that is running in the kernel mode. Where does the kernel save the user CPU state? On its own kernel stack. It is on GitHub right now. It has been. Every time I make a change, I push my changes. So in the ready to run section of the last slide, why is the user CPU state still in the kernel stack after the system call is done? Because we haven't yet returned, or haven't yet, it's just ready. So the moment we want to switch back to that kernel, to that thread, we'll pop the state up. But as long as it's ready, it's not running. So compared ready to running. That should answer your question. You should disable caching on your browser. Yeah. Yep. Okay. Now, let me talk now about what hardware does in x86 when any of the three events happen, right? At this point, I'm focusing on what hardware does, right? I'm not talking about kernel. I'm talking about what hardware does for us if the hardware is x86. Now, for whatever architecture you're writing your kernel, you have to know what happens and what hardware does for you in any of these three events. Once you know that, you can use it. So here comes what x86 does. Let's say we were running this full user level process. So this is the user stack. So we're in the full stack frame. So these are the processor registers. Usually what you have in x86 is you have your PC, program counter, you have your SP, a stack pointer, you have your setting bits and registers, configuration registers. It has a name. I forgot. So this basically says, okay, was the previous instruction, resulted in 0, and bunch of other status bits, and then other general purpose registers like EAX, I think it should. Anyways, so a bunch of other registers. Now, the PC is going to point to the code that you're running, and the stack pointer is going to point to the top of your stack. Let's say an interrupt happens. Let's say one interrupt happens. What happens? After an interrupt happens, your hardware is going to make some changes. What's going to happen? So your hardware, this is what x86 does, is going to push your stack pointer to the kernel stack. So first of all, what does this mean? So your x86 should know when it's running a thread where the kernel stack of this running thread is, so that when any of these three events happen, it starts using that kernel thread, that kernel stack. So basically, we have to save the address of the kernel stack in a register that the processor knows how to use. So once any of these three events happen, it will use that stack. It first pushes SP, it then pushes E flags, and then it pushes a PC. This is the old PC, basically pointing to where we were when this event happened. And then this SP is basically pointing to the top of the stack. And it also pushes or saves some space here for error. If an error happens, it would fill these so that when you return, you can know that an error happens. For instance, you wanted to open a file and the file didn't exist or something like that. Then PC will point to the handler. So at this point, after the registers are saved, your hardware will go through that table to find where the handler is, and then it sets PC to point to that handler, and the SP is basically pointing to the head of your kernel stack. Now, this was what hardware does. What hardware does. Now, at this point, we're now in the kernel handler, whatever handler that is. Usually in x86, kernel handlers, the first line of code that they have is a push AD instruction, as you can see here, push AD. And what does push AD do? Push AD copies all the registers, everything but PC, everything else, pushes them on the stack, everything. So after you execute that instruction, all of your general purpose, I think it saves SP plus other registers, as far as I know. So it then, this instruction saves everything. So up to this point, hardware saved these, and this is where we take a copy of the state of the processor. So now we know what registers had, or we saved what registers had in the kernel stack. Okay. Hopefully this was clear. Now, one thing that might make some of you confused is, if you look at this stack right now, you have two SPs, one SP here and one SP here. Are they different? Are they the same? Why do we have two of them? I'm going to give you some time while I'm drinking some tea and looking at the questions. Think about it. Why do we have two SPs in this stack? Okay, so let me answer that question. So yes, there are two SPs. This SP is the content of it points to the user stack. This SP, the content of it is whatever was in SP when we executed this push AD. So what was in SP before we execute push AD? This was the stack pointer. So we're going to basically have this stack pointer pointing to here. Now, why do we need this? The reality is that we actually don't need it. It's just this instruction is convenient to execute. You execute one instruction and you save everything. It saves something that you actually don't need. You actually don't need this SP, because you have, this is, first of all, it's pointing to a wrong thing that you would want to save. Second, you have already saved it. I mean, hardware has already saved it for you. So later on, at some point, you're going to execute pop AD, popping all these registers. Usually what pop AD does, it ignores SP. So it just says, oh, it's saved, I'm going to pop it up, but I'm not going to save it anywhere. Okay. I guess I can answer some of these questions. Now, what actually implements the stack? In lab, we didn't have to implement it in the kernel. Is it hardware? So a stack is memory. Your user level stack is memory. Your hardware, your kernel stack is a memory. It's basically a range of memory. Now, if you're talking about user stack, this is a range of memory addresses in user space. Kernel stack is a range of addresses in kernel space. So hardware is not going to implement anything. I mean, if you want to say memory is a hardware, so it is a region of memory. Kernel manages it. So kernel should know where the kernel stack, which addresses in memory are allocated to the kernel stack for this thread, and what range of addresses are allocated as a kernel stack for this other thread. So kernel has to know this. Now, you said that we haven't implemented, correct? You're going to implement it with lab 2. So that's that. You're going to use your allocation malloc functions to allocate user stack every time you create a user thread or user task. For kernel stack, we actually hard code it into the kernel image in our labs. So we'll just have an array of predefined array inside the image. So it's a static. So you just set the pointer. You say, I have used these stacks. Now I have this stack empty. I give the pointer to this stack to this new thread. When will quiz 2 be released? Usually we'll try to release quizzes on Monday morning. So you should usually get an email every Monday that the new quiz is ready. CSPR, yes. Does the kernel actually copy the stack or just the stack pointer? Just the stack pointer, because we're not going to touch the user stack. If other threads within that process come and mess up the user stack, that's not the kernel's fault. That's up to the programmer of that process. You should, because as I said, kernel doesn't enforce isolation between threads of the same process. So kernel is not going to touch the stack. It's going to sit where it is unless another thread comes and messes it up. But kernel is not going to touch it. Therefore, you don't need to save anything on your stack, on kernel stack. It's in the memory. Nobody's going to touch it. Can kernel threads access other kernel stacks in the same process? Kernel threads, kernel code can do whatever it wishes. So that's usually the answer. What does AD stand for? I have no idea. In push AD, I think that's what. Okay. So here is an example of a system called handler. What it does is you usually have bunch of system calls. So very similar to what you will see and what you have seen so far in our case. So we have one system call handler, that's SVC handler in our case. Then we usually look at, I mean, in our case, we just jump to the code that is inputted to the system call. Because we're assuming that users are not going to be malicious or bad behaving users. But in general purpose operating systems, you have inside your handler, you get some input from the user specifying which service it wants. So you basically vector through all the services that you have, let's say open, read, fork, exec, all the system calls. So you know which system call is needed, you just jump to the code for that particular system call. You also have to locate the arguments. These are usually on user's stack, the arguments for this system call. Let's say open this file for me or delete this file. You locate them on the user stack. You have to copy them to your to the kernel stack before you check them. You cannot check them and say, oh, everything is looking good, there is no faulty input, and then copy them. Why? Because let's say you check them, but before you copy them, another thread goes and changes them. So now all the check that you did is invalid. Let's say you have a multiprocessor and you check it, and then another thread goes and changes stuff on the user stack. So you first copy them to your kernel stack and then check it, because when it's in your kernel stack, then nobody else can touch it. Now you can check and see if everything is okay. And let's say you validate the arguments, everything was okay. Then you call your system call, you use those inputs, and then once the result is ready, you copy the result back to the user memory. so that from user's point of view, it's as if it was just a function call that has returned. Now, one thing to note here is that system calls are very expensive. Every time actually you switch to switch modes from user mode to kernel mode, it's expensive. You have seen so far in the previous slides what has to be done, right? Hardware has to save stuff, and then kernel has to save stuff, and then kernel has to handle whatever has happened. So here is a graph of, so on the x-axis you have different architectures, different processors, and each bar here shows the time it takes. Now, for the blue bars, these are just usual function calls. The green bars are get PID system call. So this is a system call, the execution time of a system call. And then the red one is the get ID system call via VDSO. I will shortly explain VDSO. I never did it in previous lectures, previous terms, but I will do it this term. Anyways, so just to compare the blue and green, you can see the huge difference. So a normal function call takes orders of magnitude less than a system call. So system calls are expensive, even simple ones like get PID. Now, what is this red one? So yeah, I guess here you have 25x overhead for system calls compared to normal function calls. Now, there are certain system calls that you might argue they don't need any kernel code. Like, let's say getting the time of the day. The reason this is a system call is because it's going to read from a register or from a memory location that is controlled by kernel, and that is time. You don't want users to control time in your system. Kernel controls it, so it's in a memory location that kernel has access to. Now, in some systems like Linux, what happens is that you copy certain safe memory locations of kernel into your user space, so that some system calls like get PID. So what is my PID? Again, anybody's PID has to be managed by kernel, but this is kind of like safe. If I can save it in user space and don't let the user change it, I should be safe. So there is a technique that you can use to run some system calls in user space. Now, this technique is very limited. The original version of it actually had safety issues because it always used the same virtual address, and that was kind of had security risks. But the other limitation of that, nowadays they randomize where kernel copies its state into the user space. But also the other limitation was the size, how much you can use. It was just one page. So usually it was able to only accelerate, if you wish, 4 system calls and not more. And that aspect of it I don't think has changed. So there are usually 4 system calls that you can run in user space with low overhead. Get PID is one of them. Okay. So it's definitely a lot more details than I just mentioned, but to just know about the concept if later on you encounter this. Okay, I think this is a good place to talk about monolithic versus microkernel OS, which probably should also answer some of the questions that you might have about what is kernel, what is operating system and stuff. So a monolithic operating system is an operating system where the entire operating system services run in the kernel mode. So everything that operating system has to do is running inside in the kernel mode, in a protected mode. All the operating system code runs in kernel mode. Now, why this was not a good idea at some point? Well, people, I mean, one thing about it is that you get a big kernel. So any code that is running in kernel mode can do anything it wants. And if the complexity of your code increases, then the chances of your code having bugs, and then if it is a kernel code, it can actually crash the system. So people started thinking, okay, maybe it's not a good idea to have the entire operating system in the kernel mode. So they started going the other extreme way of having microkernels. So they said, let's just have the most essential parts that have to run in the kernel mode as kernel mode. And then the rest of the services that the operating system has to provide, we run them in user mode. So this is what happened. So this is the resulting architecture, microkernel. So you had basic things that operating system has to do in kernel mode, implemented in kernel mode, like scheduling, like basic interprocessor communication, like virtual memory and such. And then the rest of them were in user mode. So this had advantages. Most importantly, well, now if you have a if you have bug in Unix server, it's not going to crash your system. It's outside kernel mode. It's safer. But this design didn't last long. It did not become mainstream ever. And the reason for that was its high cost. So let's say you are a user program and you want services. So you're going to do system call. What happens with a system call, you're going to go to the system, to the kernel mode, and then kernel is like, oh, this is a service that is in the user mode. So back to this service. Now this service ends. It says, okay, I have the result. It cannot go jump to the application. It goes back to the kernel and then back to the application. So for every system call, you basically have to go through kernel user. And that is very costly. And sometimes one service cannot do it all. It might actually have to go and use other services. So you go kernel, service, kernel, another service, kernel, another service, kernel, back to user. So and as you saw in the previous slide, it's very costly to do the mode transfer. So although it had really good benefits, it didn't last long. It didn't become mainstream. However, as a result of it, we came up with these hybrid kernel architectures where it's not monolithic and it's not really microkernel. It's something in between. We definitely want to minimize the code that is running in the user mode, in kernel mode, but at the same time, we don't want to switch between user mode and kernel mode a lot. So that's usually what happens in modern operating system. It's usually a hybrid architecture. So I guess I explained these. Now, I talked about user to kernel mode transfers. You can also do that from kernel to user mode transfers. What are the instances? What are the examples that we go from kernel to user? Let's say you create a new process. So once you create it, the creation has to happen in kernel, and now you want to run it, you have to go back to the user mode. Or let's say you're returning from interrupts or exceptions or system calls. Or let's say you're context switching, right? When a context switch happens, you're gonna call the scheduler to see what is the next TCB to run, and then you're gonna switch to the next thread. Okay, no questions. That's interesting. Ask questions. Questions are really good. I like them. Yes. Yeah. I got some feedback that some of your friends don't appreciate a lot of questions, but I think it's nobody's fault. I mean, if you have a question you have to ask, it's my responsibility to recognize that this question has to be answered now and some other questions has to be answered later. So I take the responsibility there. I think it was my mismanagement, but I definitely encourage everyone to ask as many questions as you have. I actually like it. If you hear me saying we'll cover this later, please believe me, we'll cover. And if we don't, then raise that question later. So don't be disappointed and stop coming to the lectures or dropping your questions. Ask as many as you want, and I actually appreciate them. Okay, so the other one that you probably have seen in 252 is opcalls or signals these are very similar to system calls. So system calls are services that the user program asks the operating system. You could think of signals as the opposite direction. It's kind of like operating system telling the process to go kill yourself or terminate or do other stuff to yourself or with your data or whatever. So this is the signal that the operating system sends to the program, and that requires a mode transfer. So once the message or signal is created and sent to the user, then you have to transfer mode and then take care of that message. Okay, so this is an example. I guess I can just jump from it. One thing though here. So here I have hardware, and then I have kernel mode, and then I have user mode. You might ask, what is this limited hardware access? Well, this is basically the access you have to the memory, the access you have to the registers on the CPU. So these are the hardware resources that you sort of have limited access to. But then there are rest of them that if you want to have access, you have to go through the kernel. And that actually brings us to the system call interface, which is how operating systems provide services to the user applications. We talked about this interface where the operating system provides an abstraction of the hardware resources it has, and the way for user programs to use these resources is through the system call interface. So if you want to use, let's say, network device, you're going to use networking system calls like create a socket, send a packet, and such. If you want to use your monitor, let's say, you have to go through the windowing services that the operating system provides. If you want to save files, you go through file system. You want to do memory management, you use mmap, you use a malloc, you use those system calls that does memory management for you. And then you want to use your processor differently, you create new threads, you yield processor, you wait for somebody else, you join on something. So you use the processor or process management system calls that are provided for multitasking, let's say. Got a question here. For VDSO, what do you mean when kernel copies data into user space? I'm actually not going to cover it much or answer this question. If you're interested, definitely look it up. I'm afraid if I spend time on this one, I won't be able to cover the actual material. But there is a lot of information available online. Definitely look it up if you're interested. Okay. Now, let's talk about device drivers. Now that we're talking about, so we talked about dual mode execution, we talked about system call interface. Now, this is the interface that the applications have to use services. But at the end of the day, let's say I want to use the hard disk drive, or I want to use the NIC the network card, I have to talk to those devices. And how does operating system talk to those devices? Through device drivers. So these are usually third-party code that usually, again, the manufacturer writes. And in many cases, we have no other option than trusting the manufacturer, because sometimes the code is not published. They just give you a binary, and you have to execute it because you don't have any other options. Let's say you want to use GPUs and NVIDIA. I mean, nowadays we have options, some options, some open source drivers, but usually you don't, and you have to just use what you're given. And the part that is painful is that you have to actually run that code in kernel mode because you're talking to the devices. Now, let's see how it happens. So this is device-specific code that directly talks to the hardware. Usually, there is a language that is used in operating system community. They say top half and the bottom half of a device driver. I guess I have a figure that makes it clear what is the top half and what is the bottom half. I postponed my definition to this slide. So let's look at what happens when when a user program calls a system call. So this is what usually happens. Let's say you request I/O, for example. You want to open a file. You want to read a file, let's say. So you execute system call read this file. Let's say 1 byte from this file. What happens is what you saw. We're gonna transfer mode, and we're gonna start executing stuff inside the kernel. Now, usually what happens is that the kernel, the handler for this system call, the system call function, looks and sees if it has already the data that you want or the service that you want in the memory. Let's say you wanted to read a byte. Somebody else had done it before, so I have a copy of it in the memory. So I have it. I don't need to go to the disk. So if I have the data that you're requesting, I can just say, yeah, I have the data. I can transfer the data to the process's memory and then switch back, return from the system call, and that's it. Let's say I don't have it and I cannot respond to it without consulting the actual hardware. In that case, this is where I'm going to actually wake up the device driver. So this is where I talk to the top half of the device driver. So we send the data to the device driver and say, okay, this application wants from this address to this address of this file, and go and pick it up for us. So the top half then initializes the hardware. Usually, this is the last portion of the course. Usually, the last weeks we talk about I/O subsystem. So usually, I/O devices have controllers on them. These are device controllers. So the driver starts talking to the device controller through some registers. So usually these controllers have registers. So and the device driver knows those registers and how they're mapped and where they are. So it sets them, and then it finishes. So at this time we're done, and then the device driver starts. Sorry, the device controller starts handling that request, reading, let's say, the data that you want to read, or sending the packet that you want to send, or receiving the packet that you want to receive, whatever that is. So once that is done, the I/O controller generates an interrupt. So I'm done with the request. Here is the result. I'm ready. So it raises an interrupt at this point. Now, what happens on an interrupt? You might actually be running some other code or whatever you might be doing. You're going to be interrupted. And then the interrupt is going to wake up the bottom half of the device driver. So this is the part that wakes up on interrupts and says, oh, the data is ready or the service is done. So this bottom half then it stores the data in the device driver's buffers. So the device driver has buffers. This is a software. So it stores the data to basically kernel space, because as I said, device drivers are running in kernel space. So the data is copied to the kernel, and then it actually wakes up the top half. It says, hey, dude, the driver, wake up. If you wish, then you could think of the top half as the device driver, sort of, and then the bottom half as something, again, part of the device driver that wakes up on interrupts. This one wakes up usually on system calls. And then here it actually wakes up again. It says, oh, the data is ready. It then returns to the kernel. And then the kernel copies the data to, so kernel routines, they copy the data to the user program, and then we at some point transfer control to the user program, and we're done. Oh, I actually had this and I didn't use it. Okay. Now, some stuff about I/O data transfer, as we talked about it. You could have programmed I/O. What does that mean? It means that for each byte that you want to transfer from the processor to the device, you need the processor to be involved. So the processor sends each byte of data to the device by executing instructions. So byte by byte, the processor sends data to the device. Let's say you're running the device driver, and the device driver is configuring the hardware. So, setting the registers, putting instructions in buffers, or let's say reading back the data from the device. It's the bottom half, let's say. Any of them. So for each byte that is transferred, you're executing an instruction. That's one way of doing it. It's simple, but as you might imagine, it consumes a lot of CPU cycles. For each byte, you're executing an instruction, and that's basically making the CPU busy for data transfer. Alternatively, you could have direct memory access. I start with hot tea, I end up with cold tea. So another alternative is direct memory access. How does this work? Well, instead of using CPU cycles to transfer data, you could dedicate a device, a controller, that transfers data for you. So all you need to do, all the processor needs to do is to initiate that controller and say, I'm going to tell the controller copy from this address to this address, or copy this much data from here to here, and then start. And now the CPU can go do other businesses. It can go and run other threads and stuff. And while the CPU is busy taking care of threads and processes and stuff, spending its cycles on things that are worth spending cycles on, the controller will transfer data for you. And once the controller is done, it raises an interrupt. Says the data is transferred, you can go and look at it. How does it work with DMA? So here's how it usually works. Let's say you're running the device driver. This is one example. So let's say you're running the device driver. The device driver tells yeah, so let's say this is the this is the top half. We're going to tell the driver we need to transfer this range of data from a file that is on the disk to the memory of this user. So basically, it's a read operation. Read this data from disk and put it in the memory. We tell the driver this first. It happens in the CPU. Then the driver starts executing. When it executes, it configures the disk controller. It tells the disk controller that you need to transfer C bytes from disk to this buffer. Then the disk controller starts running, starts handling this request. It does it differently depending on different hardware. You could have a separate DMA engine here, or the DMA engine could be inside the IDE device controller. So it would depend where the DMA engine is. But collaboratively, you need a DMA engine at some point. You initiate the DMA transfers, and what that does is that it actually reads from the disks and puts it inside the memory. And as you can see, the CPU is not involved anymore. So there is a DMA engine somewhere that is doing this. Again, in very old architectures, you had one DMA engine for all your peripherals or two DMA engines. But nowadays with PCIe Express devices, each device has many DMA engines of itself. So these are different, different architectures, different designs, different hardware. But the important thing is the CPU is not involved at any of this. So after the controller is instructed, everything will be handled. Everything will be put in the memory, and once it's done, the DMA engine will raise an exception saying that I'm done. You can look at the data that you requested. Yeah, and here is an example for network. I guess it's self-explanatory. You usually have, when your packets are arriving, these are, you could think of them as registers inside your NIC that would have addresses of DMA buffers. So when you receive packets, your hard drive basically DMAs the received packets to the memory region of the driver, right? And then once it's done, it raises the interrupt, and then you start running code. And what this does, it goes to the memory region of the driver. It copies back to kernel memory. And then you can transfer it back to the user application. But then again, the important thing is CPU is not involved. Every time you receive a packet, you don't raise an interrupt. Once you copy them back to the memory, then you can raise an interrupt, and that saves you a lot of CPU cycles. Okay, so you might ask, okay, I have been using computers and stuff. I've never called SVC before. I haven't ever executed a system call. I never think, you might say I have never, called anything from kernel. And that's correct. The reason is we have a lot of layers that would hide the end point where you actually call the system call. Usually, for instance, libraries have these layers and they do the system call for you. So you just use a user space library function, and then that acts like a stub. And inside the library function, it calls the system call. And here is a good place to bring this back to everybody's attention. If you remember, this is where we started. We said that we have all these applications and all these hardware, and we want to keep operating systems stable and portable. And the way we are achieving it is usually by having this system call interface, and then allowing some portable OS libraries to be the interface from this system call interface to our actual applications. And then we would have these, let's say, device drivers and portable kernel routines to be the interface between this system call interface and our hardware. So yeah, this is usually what we see under the hood. This is what happens. You usually have OS libraries linked to your applications as you execute them. Here is an example to, I think, end this lecture with. So let's say we have a client that is sending requests to this web server, and this web server is replying. Let's say this is a file server. So requests come for reading a file or something, and then you just send the request back to your clients. So we're going to focus on the server side. So the server program is running in user mode on a server that has a kernel on it. So you have an host operating system on your server, and here is your web server, let's say, application running, and then you have hardware on that system. The first thing your server does, it initializes a socket to receive requests. So this is a system call that comes to the kernel, and it waits here to receive. Then let's say requests come through the hardware, we receive them. We do a DMA, we copy them into kernel memory. Once this is done, an interrupt happens. Sorry. So after an interrupt happens, we return from interrupt by going back, copying this to the server, right? So saying you wanted to read a packet, here is the packet, you got it, or here's a bunch of packets that you got. Then your server starts processing this request. Let's say that it's a request for a file that we have. Now we want to read that file. We again initiate another system call here to read that file. This would initiate some device driver to go and talk to the hard drive to read the file. Once that happens, an interrupt is raised. We return from that interrupt. So this RTU returning from interrupt, we have the data, and then we can just send it with another system call to write to that socket to return to send back a result, which again will happen with an DMA. Okay, so that's pretty much it. I'm actually glad that I finished the slides. Sorry for going over time, but I'm super happy that I finished the slides for lecture 2. So hopefully on Thursday we'll start talking about multi-threaded kernels. Please don't forget to, on Thursday, please don't forget to submit your peer review forms. Again, last term, this was the main factor for students to lose grades. It's not supposed to be that way. So just by being on top of it and submitting it on time and correctly, you'll save yourself and us a lot of trouble. Okay, thank you so much. Take care, be safe. Talk to you on Thursday.